started with a continuation of the morning session after the coffee break. So the first talk will be Vincent Drach, and he will tell us about newly strong interactive sector using lattice simulations. Please.
Thank you. So first of all, thanks for the invitation. To come here and to present our results that have been obtained through DiRAC application. So what I will talk about is another application of the lattice technique that we have heard a bit about earlier today in a different context, not within the standard model, but beyond, to try to provide insights to model builders, which are, of course, building new theories to try to understand physics beyond the standard model. And so I will tell you that story, and then I will show you a few results that we have obtained. So the results. This is not working anymore. Okay. It was working 5 minutes ago, but okay. So this work, I will present results from two subgroups, which are investigating two different theories which are closely related. And here is a list of the collaborators, which are based in the UK but also abroad. And I will start by reviewing the standard model and why we need to go beyond. So let me discuss a bit the standard model of particle physics. Okay. So, okay, stay there. So the standard model of particle physics, it's a beautiful theory which describes the three interactions that we know takes place at the particle level, which are the strong interactions and the electroweak interaction, which can be split in two bits. So those three interactions basically explain all the interactions within the particles that are shown here in this table that we have also heard before. But on top of these three gate interactions that we understand very well, there is also a field that you have heard of, which is a Higgs field, which is a complex doublet of scalar with a quartic self-interaction potential, which is a very important piece of the standard model because of the so-called Higgs mechanism. It provides, on one side, mass to the W and the bosons, and on the other side, it provides mass to the fermions through what is called a Yukawa interaction. So this is to give you an overall structure of the standard model. What is really important here is that the strong sector that we have already heard before the talk about lattice QCD is non-perturbative at low energy and requires expensive numerical simulation to make prediction in that regime. So just to give you an overall view of the success of the standard model, these are standard model total production cross-section measurements at the Large Hadron Collider, so in Switzerland. And you can see the theoretical prediction in gray for in various channels to produce various particles of the standard model. You can see here, for instance, the Higgs production channel, which gave rise to the Nobel Prize, and its comparison with the experimental data. And you can see that the experimental data match the theoretical precision for all these channels. Okay, so this is an impressive success with cross-section which are spanning more than 10 order of magnitude. But we know that we need to go beyond the standard model, and there are many reasons for that. First of all, there are unexplained phenomena like the need for dark matter that we have also heard a bit about this morning, the need to give neutrino masses, the need to explain the matter-antimatter symmetry of the universe, which is responsible for the fact that nowadays we see only particles in our universe, and we don't see that much antiparticles. So these are facts that clearly indicate that we need to go beyond the standard model because this cannot be explained within the standard model. But there are also theoretical challenges, and one of them is called the Naturalness Problem. And I can summarize it by this question: is why the Higgs mass of the order of 100 GeV and not much higher, because it's a scalar particle, so we would expect to be pushed by radiative correction to at a very large mass. And another question is obviously related, is what is the origin of the parent masses, and in particular their hierarchy. So the framework in which I want to discuss today is involve a new strongly interacting sector, so a new theory which is strongly interacting at a higher scale, and which can address these theoretical issues I've just been mentioning by replacing the Higgs sector of the standard model, which caused so much trouble, by a theory which is defined at a higher scale and which gives the physics of the Higgs as a low energy effective theory. Okay, so that's the kind of game we are trying to play. And to give you an example, because of course, to give you an example, I will discuss a bit what happens in QCD, because the ideas that we are trying to implement are very similar to what is happening in QCD. So QCD, the theory of strong interaction, is non-perturbative at energy below 1 GeV. It gives rise to what is called confinement of quarks. Quarks are confined to hadrons, mesons or baryons. And it gives rise to what is called chiral symmetry breaking. Symmetry breaking, typically in physics, generates Goldstone bosons. And Goldstone bosons are massless particles, which are protected by that mechanism of symmetry breaking. Okay, so this is an interesting mechanism from the theoretical point of view that we are going to use later on. And in particular, it explains why the mass of the pion, which is the lightest bound state that you can find in QCD, which is about 135 MeV in nature, it's much smaller than the mass of the proton, which is about 1 GeV. Okay, so this is a feature of strong interactions that we'll try to reuse in the context of the Higgs by replacing the Higgs by the pion of a new theory. Okay? The effective description of QCD at low energy is done in terms of an effective theory called chiral perturbation theory, which involves low energy constants, which in principle can be computed non-perturbatively knowing the QCD Lagrange QCD theory. Okay? Because this next require non-perturbative require lattice simulations, which are, as we have heard, quite challenging. So, in the context of composite model for the Higgs, what is the roadmap? So first, the idea is to find theories, we call them UV completion, for which the low energy effective theory can mimic the Higgs sector of the standard model. So this is work that can be done in pen and paper, and make prediction in those, make prediction of deviation from the standard model, which are parameterized by some low energy parameters, such as the masses or the decay constant of this new sector, and then constrain the parameter space in view of the experimental data. But what we can do is we can even do better than that. We can use non-perturbative calculation to fix some of those parameters, some of these parameters, and provide independent constraints. And therefore, we can test mechanisms and different ideas that are played by phenomenologists to test composite model beyond the standard model. Okay, so this is what we are trying to do, or what we are doing actually. Okay, so now let me give you a brief overview of the lattice approach. So we have already heard about it a bit earlier. So basically the information in any quantum field theory is contained in what is called correlation functions. The correlation functions are given by what is called path integral, which involve an integral over all the configuration of the fields, the fermions of the gauge fields, typically multiplied by Boltzmann weight in Euclidean space-time, and weighted by a number of fermion fields, depending on what you're interested in. And the action is just the classical action of the system, which is just the Young-Mills action for the gauge field, and then the term coming for describing the interaction with the fermions. So the idea is that the lattice approach is to discretize that action and to simulate, to directly estimate this integral on a finite, in a finite box with a finite lattice spacing and a finite volume. Okay? To do this, we generate a sequence of configurations sampling the distribution of the Boltzmann weight, and we compute in the second step the correlation function. So this is the first step, first principle method, which starts from the UV description, from the Lagrangian of the, from the theory of the chromodynamics or any other non-perturbative theory, and really can relate to the low energy physics. Okay. So this is extremely challenging because typically the integral that you have to perform is a 10 to the 10 dimensional integral. It requires parallelization with frequent communications. And of course, lattice field theory has been developed over many, many years, and there are a lot of improvements that are continuously included in our codes, so that they scale very well with the volumes and the different parameters of our simulations. As we know, lattice field theory are one of the most demanding HPC problems. The code we are using is developed in collaboration by the Hindu universities, Swansea University, the Plymouth University, and University of Southern Denmark. It is designed to be flexible, so we can change very easily the theory that we want to simulate, so we can change the gate group and the Fermi implementation. And it has been used over the years to explore many different theories. And it's efficient and portable. It has been tested on many supercomputing facilities over the years, and it is typically scaled very well with a number of MPI processes. So it brings me to the calculation we have done. So composite Higgs on the lattice. So the strongly interacting sectors that we have been considered are based on two gauge theories, based on SU2 or SP2, it's the same thing, and SP4 gauge theory with two fermions in the DiRAC representation, in the fundamental representation. And this is an interesting setup because if you remember when I was telling you this story of the chiral symmetry breaking pattern in QCD, which was SU2 left cross SU2 right plus 2 SU2 vector, which is isospin symmetry. Here in that case, with pseudo-real representation, the chiral symmetry breaking pattern is different. It's upgraded to SU4 goes to SP4 and gives rise to 5 Gaussian bosons, which gives a lot of possibility to make some model building. So those two different gauge theory have the same chiral symmetry breaking pattern, which is interesting from the model building point of view because we can also try to learn how the results depend on the underlying theory and not only on the chiral symmetry breaking pattern. And if you are interested in model building point of view, you can see, for instance, this reference, which is a practical implementation of one of these theories in the context of the composite Higgs model. Okay, it's a real phenomenology of the W's and the Z and the Higgs projection and all the different channels that can be considered. And actually, you can build models based on those theories which are still viable. Okay, this is an important part. So, what were our objectives? Well, first for SU2 simulation, for the SU2 simulation, the program has been started earlier, a few years ago already, so we have already a lot of information about the spectrum, and this has been already published. But what we've done recently is to make the first calculation of the width of an unstable particle, which could be produced at the LHC. Come back to that in a minute. While in the SP4 case, led by the Swansea group, they perform first unquenched result for this theory and present these results at the lattice conference this year in June. And all these simulations, or many of these simulations, have been performed using the DiRAC facilities. So let's focus first on the first theory and then on the second one. So why are we interested in computing the coupling constant that control the resonance cross-section production of the LHC? Well, because of course, if such a particular, I mean, there are strong constraints on production of extra resonance of the LHC. They are ruled out up to TV, it depends a bit on the detail. So if we are able to predict that coupling constant, we might be able to rule out the model, or to the contrary, to validate it. This is a notoriously challenging problem on the lattice because you have to address the scattering of two Goldstone bosons on infinite box, which is very challenging. Okay, and this is what we've been doing. So this is, don't want to explain too much this plot, but this plot essentially shows the scattering amplitude as a function of the center of mass energy for one of our simulation. And it is represented in a special way so that the slope of that line gives you the coupling constant that we are interested in. Okay, so we clearly measure a non-zero slope, non-compatible with zero, and we can even say that it is much larger than what we would expect naively, or what we would expect from QCD, for instance, which is very interesting fact in its own, because there are not so many theories in which we know that this coupling can be very different. So we didn't know in advance that we could have such a different value. The fact that this slope is quite large implies that the resonance, in that, if that theory would be true, would be pretty broad. Having a broad resonance would mean that it would be quite challenging to discover by this experiment, because the broader the resonance is, the more difficult it is to distinguish it from the background. Okay, so this is the last calculation we have been doing, and so the Swansea group performed a simulation of SP4 with two fundamental fermions, and they have presented their first results, first endpoint results at the lattice conference this year. Here you can see one of the low energy constants I was mentioning before, which is pseudo-scalar decay constant as a function of the mass of the quarks, or the mass of the Goldstone boson squared, and they obtain results at different spacing, which are pretty consistent. And of course, they need to extrapolate that at zero quark mass. This is as we usually do in lattice simulation, which is sometimes challenging. And these low energy constants are really for instance, that one, the FPS, is really important because this is the low energy constant that sets the scale when you match with the phenomenon. Okay, so having an extrapolated value for this number is really important. Of course, what is ongoing is determine more low energy constant, but also compare these results with our results obtained for SU2 with two fundamental fermions, because in the two cases, I recall that the only difference is really the underlying dynamics, but the current symmetry breaking pattern and the effective theory is the same. And they have also computed the mass of other states, like the vector mass as a function of the mass of the binary squared. Okay, so maybe I can give a few more details on that. So this is a calculation of the vector measure mass as a function of the Goldstone boson mass squared, and here you can see that the result looks really linear as a function of the mass squared, which is what you would expect. Unfortunately, you can also see that there are some finite lattice spacing effect because different lattice spacing represented by these different colors. Beta here is a one-to-one correspondence with the lattice spacing size. Of course, we want to extrapolate it to zero. So the discrepancy between the different lattice spacing shows signs of differentization. So it brings me to my conclusion. So the standard model is an effective theory. Understanding the physics beyond the standard model is crucial, and there are a lot of experiments providing a lot of data about this nowadays, and future plans as well, as you know, for instance, the LHC. And I hope I convince you that lattice simulation can test non-perturbative mechanisms and guide phenomenologists to build more accurate model and more realistic model, but also provide strong constraints on practical implementation of compositics models and guide BSM searches. And so the recent progress we have been doing, I think, contribute to answer the question. Of course, this is not a final answer because these are really delicate questions, but what are the experimental signature of the underlying dynamics? It's a bit like if we were trying to discover QCD just by looking at pions. And of course, this is a challenging task, and we need to learn about what are the differences depending on these underlying dynamics. And also how we can distinguish between very similar case dynamics. Okay, thank you for your attention.
Questions?
I understand that in traditional technicolor models, the challenging aspect of this is modeling fermion mass generation, which uses extended technicolor stuff. Pretty hard.
Yes.
What are the issues with composites?
So there are also issues, okay? It's very complicated. There are many different ways to address fermion mass. In general, you need an additional sector as well, so kind of extended sector as well. Depending on your underlying theory, you can play different games. So one of the options is called, at least just by for fermion operator, adds this new scale to sector, which will be generated by an even higher energy scale. That's what we could use, for instance, naively in our model, in these models that I've, strictly speaking, shown in this talk. But you can modify a bit these models and try to include fermions in another representation, for instance, typically, and produce theories which have bound states, which are bionic, which are fermions, so that you could introduce what is called the partial compositeness idea, which is a mixing between baryon-like operator and quarks. So of course, to do that, you need to have bound state of your underlying theory, which are charged under QCD, which is weird. So you have to imagine that the theory is the top partner at 5 TeV, which is colored under QCD, which would couple to the top, for instance. And this would mix, by mixing, would generate a mass of the
Are the lattice proposals to study that mechanism, or do you need carbon?
There are a lot of proposals to do that, and I don't think you strictly speaking need your fermions, but I mean, it would help, definitely. I mean, if you really want to make a model which is really realistic, yes, probably need a couple of fermions, yes. No, maybe not actually. I think with SP4 you can add fermions,
You can add 3 antisymmetric fermions that can form a color bound state that mix with the top.
So exactly. So there is a list. Gabriele Ferretti just made a big work trying to classify all the possible underlying theories or UV completion that can implement this mechanism of partial compositeness. And so you don't need, strictly speaking, color fermions.
Any other questions? Yes, please.
So I recall that in some of the model building based on these SU2 and SP4 setups, that extra goldstone that you have was sometimes treated as the dark matter of the universe. Is that something that's still viable or something you can look at with your programming lattice calculations?
So for SU2, this I can say for sure that in what is called the technical limit, which has also a problem, indeed you have a dark matter candidate. But it's only in that very particular limit, which is probably not the most interesting. We were more interested in being in between the technical and compositics limit. So that's probably not the best way. But of course, you can always try to include other sectors to model dark matter. And, I mean, it's also interesting because This theory is typically a West zoom-in or return term, which can be used in the SIMP context to remember generally these 3 to 2 processes, which are important for dark matter annihilation.
Other questions? So can I ask you completely the next question coming from astrophysics? If you go back to your slide, you show from the result change with your beta parameter that becomes of this spacing. So what do you ideally want? Do you want your results to come faster towards each other once as you reduce
Ideally-
spacing? Is that the convergence
And-
you're looking after?
So, I mean, ideally, yes, if your lattice spacing error are small, and your lattice effects are small, then all the points should fall on the same line. In practice, you often have to do an extrapolation and you observe some residual order A effect or order A squared effect that you have to extrapolate away. Depends on the accuracy of your calculation. Of course, the more accurate you are, the more effects you see. But yes, typically, depending on the quantity also, it depends a lot of the quantity that you're looking at. Some quantities don't show much lattice discretization error, some shows really large discretization error. For instance, when we were talking about V quarks this morning, and typically heavy objects have more lattice errors, light one less many, but it really depends.